Thanks for coming, and thanks for not being put off by the rather opaque title. I'm only putting this up for the video so that people can freeze frame it. I'm not going to go over all that. So my goal is to defend the possibility of artificial consciousness against a particular argument, the diagonal argument that is based on the work of Gödel and Turing, although Gödel to some extent and Turing almost certainly would have distanced themselves from how it is used in this context. It was made famous first by John Lucas, but then found, I think, its best expression in the works of Roger Penrose. And it's particularly strong compared to other arguments against the possibility of artificial consciousness. For example, say Searle's Chinese room argument, in at least two ways. One is that it's mathematical, so it's rigorous and it's very clear. And the conclusions, some of its conclusions are extremely watertight. So that's a nice feature. And furthermore, it's not just against computational consciousness, but even against a computational simulation of conscious behavior. So Penrose stresses this point, that it is stronger than, say, merely showing that machines can't be conscious. He shows that they can't even behave as if they're conscious. So very strong. And I'm going to use his formulation, in particular from Shadows of the Mind, because it's really the flagship presentation of this argument. It's very clear, rigorous, and complete. He considers many, many objections, possible objections to the argument, and does a great job at defending the argument. So he really steelmans this argument. And he formulates it in terms of computations, which I find particularly useful, rather than in, say, the original Gödel formulation, because that makes it easier to see how it relates to AI and computation. Why? There are already many replies to this argument. Why do we need another? Well, I think the advantage of the reply I'm going to give is that it basically gives Penrose everything except what he wants. So it gives him, I'm stealing that line from Jerry Fodor. It gives him, I accept his main mathematical conclusion, G, for those of you who know the argument. I'll say what that is later. But I don't think it establishes what he thinks it establishes concerning the possibility of machine consciousness. So I'm not going to try and make some of the standard responses to his argument that other people have made, for instance, rejecting notions of knowability or soundness. And I think my reply, the reply I'm going to give, uncovers some interesting insights into computability and simulation that we might have missed otherwise. So here is my exegesis of Penrose's argument. It's very rough and ready because I'm reducing it to these three premises and a conclusion. But all the action is in the first premise. That's where the mathematics happens. It's in establishing the fact that there are questions about, for example, questions about which computations do or do not halt, that conscious humans can answer that no computer can. These are the famous non-halting results, halting problem results, or diagonalization results. But the next two premises are required in order to really get the conclusion that Penrose or other people, or fellow travelers, want to make. It's argued that from one, we can conclude that no computer can fully behave like or simulate a conscious human. And another premise is added, but fully behaving like or simulating a conscious human is a requirement for being conscious. So this tries to turn it into a claim about not just behaving like a conscious being, but actually being conscious. So therefore, no computer can be conscious. So the idea, let me just go back. So if no computer can behave like a conscious being, then a fortiori, no computer can be conscious. So here's some preliminary qualifications I want to mention. Penrose admits out front that he's only arguing against algorithmic artificial consciousness. He's not explicit, or this argument doesn't explicitly address the possibilities of an analog computational system being conscious, or even a quantum computational system being conscious. And for those of you who were here yesterday, Saw kind of his latest thoughts on that as well, which doesn't really conflict with anything that I'm going to attribute to him here. But I think he's modest on this point. I think that if my way of understanding the diagonalization argument is right, then he should claim that his argument shows that analog and quantum computers as classes of question answering systems will have the same limitations as he establishes for digital computers. So I think he might be mistaken in thinking that he's only established it for digital machines, for algorithmic machines. I'm going to skip this slide. It's for people who want to pause on the video. So let's go back to the main argument, and let's focus on this first premise. Before we can look at the mathematics of it or the results of the argument, I need to make some clarifications about how terms are being used, etc. We're identifying computations with the actions of some Turing machine. And since we can enumerate the Turing machines, we can enumerate the computations. I'm just following Penrose here. And I'm going to use those notions interchangeably as he does. So if you see a C on there, it stands for a computation, and it could be a TM on there just as easily on my screen. So we're going to be concerned in particular with Turing machines that compute the characteristic functions of properties P on N in the following way. If the TM halts on an unbroken line of ones, having been started on an unbroken line of n ones, then it is in effect saying yes to the question, does n have that property P? So with respect to P, it will be sound or unsound depending upon whether it only halts on having been started on an n that actually has the property P. Any other response, including never halting or running on forever, or halting in an improper configuration, such as a broken line of ones, any other response to that input n will be called not halting. That's just how we use that's just what not halting means. It means not halting or halting in an improper configuration. So that in a way, there's only two things the Turing machine can do in this scenario. It can either say yes, n has property P, or it can say nothing, not answer the question. Those are the only two options. Can't say no. That isn't allowed for in this contingency. So let's go to his argument proper. Although it's mathematical, I'm going to be presenting it informally. I don't think anything will be lost. So the claim is that there are questions about computation that conscious humans can answer that no computer can. How is this established? Well, let's start by looking just at what you might call the non-halting question. Will computation, the nth computation, not halt when given n as an input? That's a straightforward mathematical question. We can consider it, and you might think, well, maybe we could have a Turing machine that itself answers questions about the Turing machines, about the computations. Well, let's say we're going to try to do that. We're going to see whether there could be a Turing machine that could answer that question for all m and n. Well, to be sound with respect to that question, some Turing machine, the kth Turing machine, the kth computation, when given m and n as input, it must be the case that it halts only if the mth computation does not halt when given n as input. And for simplicity, I'm going to make that a little simpler, a little easier perhaps, by just looking at the special case of m equals n, and that's the self non-halting question, the SNHQ. Does a computation n not halt when given n as input? To be sound with respect to that question, any Turing machine that's attempting to answer that question, it must be that let's call that the computation k, it must be that when k starts on a tape of n unbroken ones, it must be that it only halts if the nth computation does not halt when given its own number n as input. That's what I call the self non-halting question. So it's a theorem from Gödel, well, not really from Gödel, but it's from Turing, let's say, and from Penrose, that no Turing machine can answer the non-halting question correctly for all n. For familiar diagonalization reasons for those of you who know what that means, but I'll show you. In particular, any candidate Turing machine, say if it has to have, since it's a Turing machine, it appears somewhere in the enumeration of Turing machines, so it has a number k. So any candidate Turing machine that has number k will be able to answer that question correctly when it's given k as an argument. So any Turing machine that is sound with respect to this non-self-halting question will not be able to, cannot halt on input k on pain of violating its soundness. It would in fact be saying, yes, I do not halt. It would be halting to say that it doesn't halt, and that's a contradiction. So if it doesn't make mistakes, that is, if it really is sound, the only thing it can do is not say anything. Whereof one cannot speak, thereof one must be silent. So there's a graphical depiction of this situation. We've got an enumeration of all the computations on the left. We've got all the possible arguments you might give to them. We're considering this non-halting, self-non-halting question. And you could say, well, maybe the kth Turing machine will solve the self-non-halting question for all n. What does that mean? Well, it means that if you give it 1, it will halt if and only if the first computation doesn't halt when given input 1. And if you give it 2, it will halt only if the second computation doesn't halt when given input 2, and so on. So it'll just be, its behavior has to halt only when the Turing machines on the reg diagonal do not halt. And the problem is, of course, that eventually it's going to meet itself on the diagonal. Eventually, it's going to get to this condition here, which is impossible to meet. It will have to halt in order to be sound with respect to this question. It will have, if it were to halt on its own input, it would in fact be saying, I do not halt when given my own number as input. Therefore, it would be wrong. It would be making a mistake. It would be saying something untrue. So if it's to be sound with respect to this question, it has to not halt when given its own number as input. Therefore, it will not be complete with respect to this question. There's a number that it cannot give the answer for, at least one number, and that number, for example, it cannot, in particular, it cannot answer the question for its own Turing machine number. And k was general. I didn't rely on anything about k, so that's true for all Turing machines n. You know right now, if you're able to follow that very clumsy restatement of this proof, you know right now that if a Turing machine is sound with respect to the non-halting question, then if you give it its own number as an argument, it will not halt. Because, since it's sound, it isn't allowed to halt. If it were to halt, it would violate its soundness. So you know right now that all Turing machines that are sound with respect to the non-halting question do not halt when given their own number as input. And that is the amazing, incredibly amazing result of this argument, because Penrose or Lucas or Gödel perhaps has done two things at the same time. He's shown you why no Turing machine can correctly halt on its own Turing machine number with respect to this question. And he's also allowed you to see that all the sound Turing machines will not halt. So you can answer the question for all n. If I say, if k is the number of a Turing machine that is sound with respect to the non-halting question, will it halt or not halt when given input k? You'll be able to say, does anybody want to volunteer what the answer is? Will it halt or not halt when given its own number as input if it's sound with respect to the non-halting question? It will not halt, no matter what k is. For all k, for all n, you know this, because you know that if it were to halt on its own number, it would be saying something untrue. And we're assuming that the Turing machines we're considering are sound. That is, they don't say anything untrue. So that's the great result here. Two things. Turing machines can't do it. We can. As a matter of fact, you just did, or some of you, or if you think about it a little bit more after this talk, you will be able to as well. So that's what I said here. Since humans can follow the above reasoning, humans can answer the self-non-halting question for Turing machines correctly for all n. you know that for all n, if the Turing machine n is sound with respect to the question, it will not halt. So humans, here's the big conclusion. It's the conclusion G that's emphasized in Penrose's book. Human mathematicians are not using a knowably sound algorithm when ascertaining mathematical truth. That is, when you're answering questions about mathematics in general, in particular about Turing machines and whether they halt or not halt, you cannot be using an algorithm because we know all of the algorithms are incomplete with respect to that question, and that you can give the right answer for all n. And many have tried to resist the conclusion by saying, you're assuming that the algorithm has to be knowable. You're assuming that the algorithm has to be sound. And Penrose gives good reasons for justifying those extra assumptions that he needs in order to make this proof. So I'm not going to press him on that. Instead, I'm going to concede. Like I said, I'm going to give him everything but what he wants. I'm going to say, you're right. Conclusion G is right. It's a theorem. But let's move on. He has more work to do before he can make the claim that 2 and 4 in particular. So what about 2? What's his argument? For 2, why does it follow from 1 that no computer can fully behave like or simulate a human? I just restate that up there. It follows from 1 that 2. Well, I think he does not show 2. I do not think, I've not seen any reason to believe 2. So I'm going to try to reconstruct. This isn't where we're out of mathematics now, and we're into philosophical, logical reasoning of an informal kind. On what grounds does Penrose think that he has shown 2 by virtue of showing 1? Well, I don't think he has, and I think that even if there are questions that we can answer correctly that no Turing machine can, this does not mean that Turing machines cannot perfectly simulate us, cannot gain the same behavior as we can. And that's because behave like, or same behavior, or simulate, or same, those are, maybe Penrose is using a notion of sameness that is not relevant in here. So I'm going to try to show you there's a notion of sameness in which Turing machines computations can perfectly simulate us, and therefore 2 is false, or 2 has not been shown at least. So to see what's wrong with inferring 2 from 1, note that the non-computability of that self-non-halting question for Turing machines and our apparent ability to answer it both arise solely from the fact that Turing machines or algorithms or computations are referred to in the self-non-halting question. They're mentioned in that question. The question was, does the nth Turing machine not halt when given input n? So in the question, it's not about does 2 plus 2 equal 4, or are there an infinite number of primes or whatever. Instead, it's the question about Turing machines. And then now you're giving that question to a Turing machine. So no wonder you're going to get some self-referential problem that prohibits a Turing machine from answering correctly. So the insight here is related to an insight from Whiteley, but I think my reply is substantially different from his 1.5-page response from the 60s. The idea here is that if we define a comparable question, but instead of making reference to Turing machines, we make reference to persons, let's call it the person self-non-halting question, then the same discrepancy between humans and Turing machines arises, only in reverse. And then I'll show why that changes everything. So let me go over that in more detail. So here's the person self-non-halting question. It's not a formal mathematical question. It's not a mathematical question because it involves people and sentences of English, right? But it's still a well-defined question, or it's a well-defined approach to generating questions. We can enumerate all the questions of English of finite length. We can enumerate all the people who are alive. Suppose your number is n. And we're going to play a game. I ask you questions by giving you the number of the question in the enumeration. You've got the list or the way of generating those questions. You know how to go from a number to the question in English that it numbers. So I give you that number, and I want you to answer the question that the number denotes. And you can never give a false answer. and you can only answer, or you're not allowed to give a known false answer, and you can only answer yes or remain silent. Those are the only two options. You can't say no, you can't say maybe, you can't say something else like I reject the whole framework of this system that you're forcing me into. Okay, you can't do that in this game. If you're going to play the game, if you can only be considered to be playing the game if you never give a false answer and you can only answer yes or remain silent. So I can ask you question K. Question K happens to be this question. Does the nth person not answer yes to the kth question? So it's a question that's about itself. It's question K, it refers to the kth question. And it also refers to you. So when I ask this question of you, when I say K, N, what's your reply? Well, you go K, oh, that's the question. Does the nth person not, oh, that's me. Do I not answer yes to this very question? Well, in effect, what the question is your answer to this question not yes? And we know from playground, perhaps, if you're kind of a nerd who did this on the playground, your answer to this question, you can't answer that correctly by saying yes, because you'd be in effect contradicting yourself. So you have to remain silent. Those are your only two options. So here's an example of a task, a set of questions that you will be. We know that you can't answer this question correctly for all K and N, or I could even make it similar by making K always equal N. But anyway, you cannot answer this question correctly for all K or all N, because you meet yourself on the very same similar kind of diagonal. Therefore, you must remain silent, and therefore you are incomplete with respect to this question. But what's interesting is to note that there's no reason why a Turing machine couldn't, maybe it's just a lookup table, because we have a finite number of questions, a finite number of people. There is a Turing machine that does give the right answer to the person's self-non-halting question for all K and all N, because unlike for the self-non-halting question, there will be no contradiction in it so doing. It's not going to meet itself on the diagonal somewhere, because we're not enumerating over Turing machines. We're enumerating over people and questions of English. So there's going to be no contradiction. So our inability to answer the person's self-non-halting question is an artifact of its reference to persons, just like the inability of any Turing machine to answer the original self-non-halting question for all N is an artifact of that question's reference to Turing machines. Now you might think, perversely, that, oh, this just strengthens Penrose's point. He established one difference between what humans and computers can do before, and now, Ron, you've just shown us that there's another difference. We can't do this thing, and Turing machines can. So the class of abilities that we can perform, and the set of behaviors that we can engage in, and the set of behaviors Turing machines can engage in, are even more disjoint. But I think that is perverse. That it really all depends on how you look at it. And so I think that the best conclusion here is that even if the token inabilities of Turing machines and people differ, the inabilities may be of the same type. And I think that's clearly what's going on here. What do I mean by that? I'm saying the behavior of Turing machines and people may be extensionally distinct. Yes, there are functions we can answer correctly, but Turing machines can't. Yes, there are questions Turing machines can answer, but we can't answer correctly for all N. But they're intentionally identical. What do I mean by that? Let me give you a little analogy. So I'm Ron. Nice to meet you. Suppose I have a twin named Dawn. Well, note this. I can't sit on Ron's lap. Right? I can't sit on my own lap. But Dawn can sit on Ron's lap. Well, yeah, he can do that. Oh, so Dawn has some ability that I don't have, right? Dawn can sit on Ron's lap. Well, yeah, if you want to look at it that way, but look, Dawn has exactly the same type of limitation. Dawn can't sit on Dawn's lap, but Ron can sit on Dawn's lap. So really, Dawn and I, as you might think, because we're twins, have the same reflexive limitation, that of not being able to sit on our own laps. And I think that analogy suggests what the correct way to look at the Turing machine results are, the non-halting question results are. that sometimes y having different abilities or properties from x in an extensional sense, sometimes it's no barrier to y being a perfect simulation of x if nevertheless they have the same abilities on the level of types or on the intensional level. I'm going to skip over the rest of that slide. Specifically, for x to simulate y, it's not required, I'm claiming, for x to compute the same function as y. And here's a side point about universal machines. The existence of universal machines does not defeat this point because universal machines are not actually computing the function that they're simulating. They have their own Turing machine number, so they are distinct from the computations that they're simulating. They are not identical with them. But anyway, let's move on. Don't have time for that. So even if there are, check my time. Okay, I'm over time. All right, this is my last slide. So even if there are extensionally construed functions that humans can, but Turing machines cannot answer correctly, this does not imply that Turing machines cannot perfectly simulate human behavior. In fact, both humans and Turing machines have exactly the same intentionally construed limitation in this area. Neither can solve their respective non-halting or self-non-halting question. So it has not been established, I would say, that Turing machines cannot simulate human intelligence. So we have this possibility that remains open. Turing machines can compute functions or employ algorithms that constitute a perfect simulation of human behavior, even though humans are not themselves using that algorithm. So that is the end. Thank you.